Hello everyone, now we have a great opportunity for an industrial tour. We're visiting our sponsor and a partner, so you have a chance to taste the PEF, which is post-electrical fields. So let's go and get around, check what they have, and enjoy it.
Sergiy, hi. Nice to see you.
Yeah.
Come for the tour. Hello everybody of the industry tour. Follow me, I'll show you around.
That'll be great. Thanks a lot. Follow us. Great that you invited us for a nice industrial tour. Hopefully we'll enjoy it. I'm pretty sure we'll enjoy it. And we have with us all the participants of LCA Food 2020 conference and also all the participants who are joining the tour, who are joining the workshop. And we all want to see everything you have. We want to see the machines. We want to see how you do, how you operate. So please tell us.
Yeah. Okay. Yeah, welcome everybody and hello to Sergiy and all of you. Elea is a company dedicated for pulsed electric field systems. So we market them, technology developed at DIL on our campus here. And we are marketing that technology into the food industry with a focus on some industry sectors like the potato industry, the juice industry and the drying industry.
Oh, great. So, will you tell us something about what we have on the table? Like, what is the main application points for the post-electric fields, for the PEF in the short term?
PEF has its major application at the moment in the potato industry. So it's used in French fries as well as in chips processing out of a number of reasons. The major reason is it's improving the cutting, and that cutting improvement then has a number of benefits in the subsequent processing, which are related to the product quality, but are also related to savings in the process. And the savings are in particular related also to environmental benefits, as they more or less are in the area of water and energy requirements reductions.
Well, so when you say savings, those are savings of materials, resources, or energy, I guess, water, or...
all of that. The cutting improvement, I'll give you an example in a minute, or show you live here. The cutting improvement results in a higher yield. That is one of the major benefits. But it's also replacing a technology which was earlier used called preheating, so a thermal cooking process, which also was requiring more energy than the PEF process. But at the end, yeah, theory is great. I think it's best just to treat a few samples. And that's what you see here. The application is mostly done in potato or sweet potato, so we can just process a few of those. The machine we are going to use here is our smallest industrial system here. That is a continuous system doing 6,000 kilograms per hour or 6 tons per hour in that industry sector, where a PEF system is on the back, or a PEF pulse generator, and on the front there is an application side. Maybe we can switch it on. I'll ask Julian so that I can stay here. We will put some potatoes through, and then afterwards I just would show you the effect this has so that you have a basic idea.
So this machine is used for French fries production, or for...
That is a machine used for French fries production. If the French fries producer is on a small scale, 6 tons per hour for them is a very small scale. In the potato chips market, this is a kind of a standard size. These are typically smaller lines. We hear the machine running now. It's making some noises. That noise are the actual pulses. So we are pulsing here with approximately 20 kilovolts and an energy input in a range of 1 kilojoule per kilogram usually. And the pulses are in a frequency of several hundred pulses per second, and that's also the sound we are hearing here. As the process is continuous, the potatoes are now going through underwater. We need the water as an energy transferring medium, and with residence times of a few seconds in that belt, they are coming back out and are treated. We just switch off the system so that we have less noise. We have the samples of the product, and yeah, I think it's best if you cut them and find out if you notice any difference here.
So I should close my eyes then, but I wouldn't try. So this is treated, this is untreated. They look the same, just one wet, and
it's both still a whole potato, yeah.
So just probably put it aside so we can
those aside.
see.
The effect is not in a way that we are meshing the potato, and you notice they are gonna be cold still. We are only applying 1 kilojoules per
I'll
kilogram
start
energy.
with the untreated, just to see.
How does it cut?
The knife is very sharp. But yeah, it cuts good, normal potatoes. Nothing exceptional. Yeah, it cuts smoother, you can tell, and there's more moisture coming out. You also can tell it by the side here. Yep.
So you have visibly seen that effect of the water release, and that's also the underlying effect we are seeing here. We are opening up the cells, the turbo pressure is released, and that release of the turbo pressure is causing a softening. And that softening, yeah, you can ask what is that good for? That's good for really improving the cutting, which normally is not done with a knife like that, not with a sharp knife. With something like what we see here, the potatoes are shot through a grid at high speed, and that causes a breakage of the tissue. And again, or in addition to the breakage, there is coming a starch loss, and that starch loss is typically in a range of 1 to 2%, which is a yield loss, and this is what we harvest with PEF application. The yield is increasing by 1 to 2%, which on a standard line, which is between 200 and 500 million tons per year, makes 1% of that a really big number.
Yeah, it's a considerable number of less waste, totally.
Yeah.
So then if such knives are used, then if you cut easier, then probably you don't change knives that often in the industry. Does it?
Yes.
Does it help anyhow?
That is a side effect as well. And as you just cut by hand, we can also do here on that cutter. So it's possible to cut the potato without the pre-treatment.
Okay. I'll take this
but
one.
This one is going through like butter.
Yeah, it is also visible.
Yeah. And the same effect can also be seen then on whole strips, where you see an effect that non-treated is breaking very easy, whereas a treated one is not breaking. Yeah, so you get a higher yield.
So this is untreated or treated?
Yeah.
Oh, this is untreated.
Untreated, yeah.
And then the treated one, I can,
you can bend it further. You can break it if you like, but it's breaking much less. So that's also contributing to a yield increase.
Yeah, it takes efforts to break.
Yeah.
No, actually.
Yeah. So yes, as said, the cutting is easier. The knife lifetime is more or less doubled, so that is less work for somebody having to replace or to sharpen the knives. But from an energy perspective, the major benefit would be that the technology which has previously been used is a heating to 60 degrees centigrade with a holding time of 30 minutes. And depending on the amount of heat recovery you are using, that would be somewhere in a range of 50 to 90 kilojoules per kilogram.
50 to 90 in comparison to 1 to
1. Yeah.
Okay.
And that is more or less the major energy benefit. As we are less heating, we are also not in water long. You have seen that takes only a few seconds, and that is why we need less water also for the treatment. When you cook a potato, a lot of the minerals is leaking out into that water, and you have to replace that water quite often. Here we have a much lower water replacement, so also 90% reduction in the water requirements would be coming up.
Okay, so water treatment savings.
Yeah.
Anyway, that's also pretty nice. Okay.
So,
do you know the numbers by heart on the water savings?
More or less. The numbers, we have the picture here. We have created a setup or a basic sheet on the savings to be expected in terms of energy saving and water saving. This is data from a line, an average sized line, 25 ton per hour of potatoes to be processed, which more or less gives 12.5, 13 tons per hour of French fries to be processed. That means per year we talk about 250 million tons of, 250,000 tons of potato per year. That is the number behind it. On water savings on such a line, this makes approximately 25 million cubic meters, or in a bit more user-friendly word, around 171,000 bath tubes full of water would be the water saving. This is approximately, dependent on the overall size of the factory, somewhere in a 3 to 5% range of the water consumption of such a French fry factory.
So pretty much what you're saying, that the installation of one middle-size machine could save enough amount of water, which would be enough for a city to take a bath.
Yes.
Oh, like city like Osnabrück, and probably even bigger, to take a bath.
Yeah.
Everyone, all the citizens in one day, or maybe even more. Okay.
Yeah. I mean, those huge numbers come as those factories usually also have a very high throughput, and that is adding up then to high numbers. If you look at the energy requirement, replacing a preheating by a PEF system is saving approximately 10 million kilowatt hours on such a line.
Wow.
That's also a big number. The correspondence would be 1,363 times driving with a car around the globe with an electric car.
Electric car, yeah. That was my question about here. I spotted it, yeah.
So that is a lot of electricity and energy saved here. Again, this comes from the low energy requirement of only 1 kilojoule per kilogram, which the PEF treatment has, and which is the major benefit. Again, we have to put that in perspective. In the overall French fries processing, that is not halvening the energy requirement, or so. That's again in the range of some percent, 3 to 5% of the overall energy consumption of the whole line. The major energy requiring steps in such a line would be the frying and the freezing, but we are substantially contributing here. Yeah.
So the savings at the processing part also contributes to energy saving for frying, you mentioned. How does that work? I mean, you have potatoes and they So
as we have seen, the water is leaking out of the cell. So if you put that in a fryer, the water is better available, and therefore the water is coming out easier and faster, which means we don't change the enthalpy of evaporation. We are removing the same amount of water in a little bit faster time, but we will use the energy better and use the energy in a shorter time, which means we have less losses to the environment, and therefore we also have savings. On a frying line for chips, we typically have a 10% acceleration. On a frying line for French fries, we have a little bit less of that effect, 1 or 2%. Why? Because here there's also a blanching step. And whilst PEF is releasing the water, the blanching step is binding the water again into the gelatinized starch. So PEF is opening the doors, but a number of the subsequent steps can also have a very strong impact on the behavior of the line.
So freezing also would have the same effect as frying on easily.
We see effects on PEF on the speed of freezing. We see them less in a French fry than on other products, which will be touched later on a bit. The reason why they are not so much seen in the French fry world is French fries contain a lot of starch, which is during blanching binding the water, and then the mobility effect is gone. PEF is not doing more or less than opening doors and allowing mobility of water. But if you look into freezing, drying, frying, mobility of water is also via convection mobility of energy, because that water is moving and is also transporting the energy. And as long as the water can move freely within a product, the energy transfer in that product will be improved as well, because we have convection in addition to conduction.
So you mentioned that the water, you're opening the doors in the cells and the water is leaking out, but then when you fry it, wouldn't the fat go inside the potatoes, inside the tissues, and would be stored there? So would it lead to the higher absorption and accumulation of fat in the product? Or
we had this assumption, and this was one of the major worries we had in the beginning. Opening up the cells, allowing more oil in during the frying. There are two effects which are preventing that. The one is, whilst we are frying, water is going out. So this is a countercurrent flow to the oil income. So as long as water is leaving, there can't be much oil entering. That makes it important, and is another reason why we are shortening the frying time. If we would fry for very long times, once the water outflow is stopped, there is the option for fat to come in. And the second effect, which is very important and has been found out in structural analysis using physical labs and physical technologies, the cutting improvement leads to less cracks in the strips, and the actual oil uptake is not happening over the surface. The actual oil uptake is happening in the capillaries. So once we break the tissue less during cutting, we have less entry points for the oil, and therefore we have less oil uptake. So on a standard French fry line, you would see approximately 10% less oil requirement on the frying line, which at the end, if you want to receive the total amount of product again, is replaced by potato. But the oil reduction has a number of benefits. One is a nutritional benefit. 10% is not allowing to call it a low-fat product, but it's still less
fat,
oil to be used. And the other side effect is a cost factor, because potato usually is a factor 1 to 4 lower in costs than the oil would be.
So there are also benefits.
There are benefits of that as well. As you just said, does that leaking have benefits in frying and oil uptake? Just want to put out as well, we want to open the cells, but we don't want to open the cells too much. That is bringing us back a little bit to this discussion yield. If we are opening up the cells too much so that the starch kernels would actually go out of the cell, then we would have a contradictory or negative effect here. We are benefiting from the effect that water molecule is smaller than sugar, is smaller than starch. So by controlling the pore size, we can allow the water out, possibly the sugar out if we are interested in that. But we can maintain the pore small enough so that the starch is staying in, because this, for a French fries processor, is yield and is what he's selling.
So how do you control the pore size?
The pore size is directly related to the energy we are applying. So I mentioned 1 kilojoule. That is an energy input where we are opening pores, some nanometers of size. If you would be interested in larger pores, like in other applications where we want to get color out of grapes, which we will talk about later, then often higher energy inputs are applied to generate larger pores. Here we are only interested in a little bit of softening, not too much starch release, because the starch is sold in the form of French fries. If we would get out the starch and put it into the water, you could recover it from there, but this is extra efforts and water usage. And this basically would be then a starch factory, not a French fry factory.
Yeah, I also mentioned the savings in terms of energy, then also 10% of oil, there was a frying time, also I guess pre-treatment time, that was all you said. So at the end it should result into some savings in economical approach. So I guess that makes the system quite favorable and devout.
At the end, energy, water savings are used from sustainability aspects, but also cost savings to make the production more efficient. From commercial perspective, PEF in the French fries is the savings are carrying the costs of the machine, no doubt. How fast such a return of investment is pretty much dependent on the scale of operation. PEF is a technology which works very well in a large scale. We started with the large scale machines. We are now downscaling the systems into more niche specialty applications. Typically, on a large-scale installation, the return of investment is done in a year or something like that. So it's almost a kind of no-brainer. When you go down in scale, like on that machine, we've seen 6 tons per hour. We are mostly in times between 1 year and 2 years. When we are smaller, the machine are not getting linearly cheaper because you still have the safety, the control mechanisms, and so on. But that's at the end our ongoing research work at the moment, allowing more PEF use in decentralized situations, smaller markets, smaller products, cooperatives of farmers, and similar applications like that. Because we've seen the huge commercial but also sustainability benefits on a large scale. And I think it's worthwhile to roll that out also into much more applications on a smaller scale. It brings more applications for us, clear. Us as a machine supplier, we have a natural interest in having more applications, but also is multiplying the environmental benefits we're having with that technology.
That's something that is absolutely of most interest for our audience. So the main applications, as you said, was potatoes, sweet potatoes, for French fries production.
Yes,
and chips, I guess, because chips are here.
Exactly. We just spoke about French fries, but let me just take a sweet potato as an example. That is sweet potato with and without PEF. Yeah, it's going to be dangerous already. I'm just trying to slice that thin so that you see that effect of breakage here very well. if you take that one, that is immediately breaking. The PEF one again has the same kind of effect that you don't break it. That allows, again, the same benefits of yield and so on, but that also allows to cut different shapes, and that is what is very interesting for the crisp industry. You can cut thin shapes like that one. You can try if you want.
Totally.
Which brings a completely different crust and crispiness. Yeah, very crispy.
Very.
You can cut those wafer cuts without any breakage.
And not fatty.
From white potato, from sweet potato, without any breakage. And again, the breakage here, or the lack of breakage, means you get a lot of intact pieces, so you don't have to sort out fines, which are going to animal use otherwise, or going to lower value products. You have a lower oil uptake because of the good surface properties here, and it allows to do that from a number of raw materials which otherwise you couldn't slice, like sweet potato, like cassava, like manioc. So this is not even harvested at the moment, the full potential of PEF here, to produce local snacks out of rooty, starchy material in different countries. Where potato maybe is not familiar so much, that is a lot of options for new product developments coming up in that industry sector.
So the sweet potato chips and French fries on the market was probably processed by PEF. Can you say like that?
Yeah, on French fries, I don't have an exact number, but we have a good overview who is using PEF. And definitely, if you go in Europe or in the US or Asia into a standard fast food or restaurant, you will have PEF treated.
But for sweet potatoes?
Same on sweet potatoes. It's very difficult to do sweet potato fries without PEF, because you've just seen when I tried to cut it, it's almost impossible without. And if you try to preheat the sweet potato, it's either getting too soft or it's going to be too hard. It's very difficult to hit the spot. Why is it so difficult with heat? Heat is propagating from outside to inside. So the half-hour cooking time is needed because the heat takes so long to get from outside to inside. So a tuber which is thicker takes longer, a tuber which is thinner takes shorter. So however you set your equipment, it's not going to be right. PEF has the benefit of being volumetric, so the treatment is the same inside and outside, and that's what I find fascinating about such a different technology. Different mechanism of action allows a more targeted approach. So on sweet potato fries, they would be, coming back to your question, treated as well. But when we talk about chips, this is an upcoming market. We have approximately 30 machines running in the potato chips or crisps industry, but this for us is a fast-growing sector. There's plenty of machines out there. This is a very decentralized market. Why is quite obvious if you see that there's not much chips in that 1 liter volume here. So that is a product which doesn't transport very well from a sustainability perspective, transport worthiness. So that means more decentralized production than, for example, French fries. We needed the smaller machines. You see the example back here. And since we have that machine available, dedicated for that market, we see it's taken up by the industry very, very well.
So you're also opening some possibilities for the small scale SMEs to do some small scale nice products.
Yeah, we do all kind of trials. I mean, that is products well established that PEF works. The interesting bit with those machines is then you can, because the technology is available and this has changed a lot in recent years. Earlier we had to find an application and had the question who is developing the machine for it. Now the machine is available, so we only have to find the application. And the smaller scale machines help a lot to try out different things on a pilot level. Yeah.
Oh, very nice, interesting. So you mentioned about the different application cases, not only French fries and chips, crisps, but also potentially something else?
Yeah, there's a number of applications. Potato is a good example for a plant-based product. The effect of PEF is not limited to plants. That works for animal cells, meat cells, but that also works for bacterial cells. Can open up any biological cells, so wherever a mass transport improvement is of interest, or where microbial inactivation with low heat input is of interest, that works. And that's something we would like to show you as well, but I would use add two of my colleagues here, Claudia Sima, our research manager, and Julian, liquids application specialist in the team, and they would guide you through other applications. I feel we only have touched the surface of what is possible with PEF so far, so have fun with that.
But thank you, very understandable, very clear, and hopefully we see us again.
Welcome.
Thank you. Oh, hi, Claudia. How are you doing?
Sergiy. Fine. Hi.
Yeah. So please tell us a little bit about yourself first.
Sure. So first of all, a very warm welcome here to Elea. So we are very proud that you are here and want to know a little bit more about PEF and all the different applications. So I think it's also interesting for all the audience. So welcome to the audience as well from my side. My name is Claudia Sima. I'm the R&D manager here at Elea, so dealing with all the different applications, all the research projects going on, so finding out what's possible with PEF and what's not possible with PEF.
So about what's possible with PEF, I heard from Stefan that we can treat some liquid materials, specifically for maybe microbial inactivation. So please tell us, I see a lot of juice here.
Yeah,
nice,
I think you can see already what's all about here. It's about microbial inactivation, and the overall aim is to have a shelf-stable premium juice.
Okay, why is it premium? Why do you consider it's premium?
Exactly, what is premium? So I think the best is you taste this juice and then you will tell me what is premium.
Okay, so this is PEF treated or not PEF treated juice?
Just tell me.
Oh, it's hard to tell. I need to have a benchmark. I need to have a
You need a benchmark, of course. Then you have a standard. Of course we have a standard as well.
This is very good.
So, but very good. What does it mean for you? I mean, it's a premium juice, but what does it mean, premium?
It tastes like freshly squeezed, sweet, nice, full flavor juice.
So, like freshly squeezed juice?
Yeah, freshly squeezed juice.
Okay,
exactly.
Perfect.
So, do you have something not freshly squeezed juice?
This is not freshly squeezed, and now taste the difference.
It tastes a bit different. I mean, it's still good juice, but maybe there is a bit of cooked flavor, but it's kind of like, called pasteurized flavor juice, pasteurized juices or pasteurized milk also kind of have this flavor when taste raw milk and pasteurized, that is kind of the same. But yeah, if you tell me, I would prefer this one.
That's good. That's a fresh one. So. And PEF has now the advantage that you can produce this kind of juice shelf stable. So normally if you press your juice at home, there's a certain shelf life because there are microorganisms inside, some certain bacteria, and they start to grow after a certain time. And they start, they are not good for your health, so it has a certain shelf life.
But thermal treatment or pasteurization also does the same, right?
Exactly.
You get a stable, shelf-stable juice. So why are the companies interested in PEF for juice?
Okay, so traditionally, as you already said, the products are heat treated. So the product is exposed to a high temperature for a certain time, and the microorganisms, bacteria are killed in the juice. But this temperature has also an impact on the quality. So certain ingredients which are responsible for the flavor and also the health, so all the vitamins inside, they are destroyed by the temperature.
And PEF?
And PEF not.
Okay.
Because PEF, remember the animation we had before? So PEF, it's a physical principle. So the cells, whether it's a cell from the potato or here we are talking about bacteria, they are affected by the electric field. So we are affecting the membrane of the microorganisms by the electric field. So we are just porating the membrane and there's no heat involved. So because of this physical principle, the bacteria is in the healthy ingredients were not affected. And that's why we can achieve this shelf-stable premium juice.
So you basically kill bacteria, but you don't sterilize juice per se.
Exactly. Yeah.
Nice.
So now you know the secret.
No, I know the secret. But you also have some other interesting products. Can you tell maybe,
Yes.
for the range of applications, not just orange, I believe it was orange juice, right?
Exactly.
It was not just orange juice, but also...
Yeah. So you can treat various type of juices, smoothies, fruit purees, even concentrates. So starting from a red one with different kind of berries, carrot juice, but also here some other types with banana. Even if the juice is a little bit thicker, like it is here, it's no problem to treat this by PEF. What's another kind of very interesting application, which is quite new, which you maybe also saw already in the supermarket. There are some upcoming products which are a little bit blue, containing blue.
Yeah.
And they are produced with the blue colorant from spirulina algae. So you can see it here.
Is something
Exactly, it's very blue, and this blue is very heat sensitive. You can have it, and no, leave it here.
Okay.
And this blue is this colorant is very heat sensitive, so it's not easy to pasteurize this colorant. And by using PEF, you can have a shelf-stable colorant and can use it for different kind of food products like gummy bears or also juices. So this is a mixture with the blue one. If you want.
Which juice is that?
This one contains apple, a little of banana. That's why you have this dots here, and the blue colorant.
This blue color. So,
and it's very tasty.
So using just a bit back before we move on. So by using PEF system, you can really preserve blue colorant from spirulina. Which is a very expensive product, right?
Exactly, it's a very expensive product, and PEF can be used also in a different way for spirulina, because the blue colorant is extracted from the algae. So an algae is a cell, so you can use
to extract
the colorants to improve the extraction. So this is just a side effect.
Yeah, let's try.
Let's try. It's very tasty.
This is again banana, blue colorant, and something else. That's something tricky, no? Apple. No?
Apple, yeah.
Sorry, guys, you cannot feel it, but it's very delicious. So it's not on the market.
Not yet, but will come.
Very tasty.
Very tasty, and I think it's very fresh. Very fresh flavor.
Yeah.
Yeah.
I can imagine. So also smoothies you mentioned there.
Yeah, smoothies. Every kind of product which is pumpable.
It's also from the cabbage.
Cabbage as well. So
ginger smoothie.
Ginger smoothie. There are also some kind of, which is now very popular, this type of ginger shots.
Yeah.
So you can produce this as well with PEF.
Oh. Then I think it covers the part, and I think it's very interesting and can help also with in terms of environmental part. If you preserve fresh premium juice for a longer time, that might be certain benefits, and also the health related as well.
Exactly.
Very nice.
Yeah. So I want to share a little bit more about the production using PEF in the factory. And how this looks like. So you've seen this nice machine for potato processing. Of course, for liquids, it looks a little bit different because it's quite clear.
So liquid like that,
Exactly. So we need a pipe system, and within the pipe system, we have two treatment areas installed where the juice is exposed to electric field and the microorganisms are inactivated. So it's as you can see here, also these systems are quite easy to install. It's like a plug-and-play system, and can easily integrate it into the production lines. And due to this extended shelf life, there are certain advantages also regarding sustainability. So if you now extend the shelf life of the juice, you have less waste because you can produce a larger amount of products because of this longer shelf life. Then you have also less cleaning times in between, so there are certain benefits.
So, I mean, in terms of speed, what's the ranges of a speed throughput of products? I mean, taking into consideration probably the machines in different sizes, I would imagine.
Yes. So we have different systems available depending on capacities, starting from a very pilot scale with about 50 liters per 50 liters per hour is the pilot scale, up to 5,000 liters for industrial scale. And if we run the highest scale unit in parallel, then we can achieve even higher capacities.
So the speed is not limitation and throughput is not limitation.
No.
And
so it's really industrial scale. It's
nice.
The industrial scale is very high for these type of juices.
Sounds great.
Yeah. The biggest advantage for using PEF for juices you can see here on this graph. This is showing the temperature time profile of a thermal process, and in blue here the PEF process. So you can see here that the thermal one reaches a temperature of more than 80 degrees Celsius. So it's destroying the taste, all the healthy ingredients. With PEF, you have here first a preheating phase, then the PEF, you have a temperature peak, and then the cooling phase. You can see here that there's temperature involved. This is because we are adding energy. So as Stefan already said, so for treatment of potato, we are using an energy input of 1 kilojoules per kilogram, for example. But for juices, as bacteria are way smaller compared to a potato cell, we need energies around 80 up to 100 kilojoules per kilogram. And this is resulting in an increase of temperature.
But obviously it's probably less than those needed for thermal one.
Exactly. So the thermal heat load of the product after PEF process is lower compared to the thermal one. And this is giving the huge benefit for the juices.
Time range, does it matter?
It's
I guess, is it preheating stage required at all?
There is a preheating required because if you preheat the juice, the bacteria is more sensitive towards the treatment. That's why you have here the preheating phase. And this can be, of course, shorter. So in the end, the PEF treatment can be
the PEF treatment itself is relatively short.
Exactly. It's for a very short time. So you don't need a holding time.
It's milliseconds.
Exactly. It's in the range of milliseconds. So to summarize, we have it here. So as you already saw, low temperature processing, which is quite important. It's a continuous working process. So for liquids, it's quite important that it works continuously. It's easy to integrate. So you have the system, you just connect it, plug and play. Which is also important, it has a small footprint, energy efficient, low cost, and which is also important, any packaging material can be used. So you can fill your juice in glass bottles, but other type of packaging material is also possible. So
the selection of packaging material can also play a role for a more sustainable product at the end.
Exactly. Yeah.
Very nice.
Good.
Yeah.
Okay.
Then thank you, Claudia.
You're welcome.
It's a pleasure. I'm gonna move on to the next stage. I still
more.
have some nice stuff there. So we see us more.
Have fun. Bye bye.
See you.
Bye. See you.
And hello, hi.
Hi, Sergey. How are you? I'm good.
I'm good. So
welcome to you guys as well.
And our next station, and it looks already pretty fascinating on what I can try here, and hopefully you guys will enjoy it with me. So tell us what do you do, what is interesting in Elea, and then we hopefully start with the tasting.
Okay. So first of all, my name is Julian. I work in the R&D department at Elea, mainly focusing on the liquid applications, but I'm also working in extraction, and I'm going to show you a few examples what PEF can do in terms of extraction and making processes more efficient, which also contributes to a more sustainable approach of production.
Yeah, totally. So you basically, when you say extraction, you can extract something more from plant materials.
Yeah, exactly. As Stefan and Claudia already explained, what PEF is doing, that it opens the cell membrane. So we're opening the door. We're opening the door for everything that wants to go in or out, and we can do that for a lot of different things. Examples would be carrots, apples, horseradish, or grapes, or you can use olives as well. One example would be when you're extracting juice from apples. What would you imagine when you open the cells before you extract the juice from the apple? What would you expect to be happening?
more juice.
Exactly, you can see more juice. As you can see here, this is the same amount of apples that we've pressed. So this is the untreated sample, this is the treated sample. You can see that there's slightly more yield. And this is only small volume, but if you scale that up to a couple of tons per hour, that can be quite an impact in the production.
I would say 10-20% is
10-20 is quite a lot. We can sometimes see that on a lab scale, but something up to 10% is realistic, I would say. It gets more efficient, especially when you're using quite hard materials like carrots, because that is quite difficult to get the juice out. You can even use sweet potato, which is difficult. It is quite dry, but you can actually, when you PEF treat it, you can squeeze the juice out by hand.
So how does it taste, the sweet potato?
Sweet potato juice is quite nice, actually. It's sometimes used in different smoothies to add a little bit of sweetness without using sugar. Just using sweet potato juice to create a clean label.
Nice. So there's another idea for the market.
Yeah, definitely. Yeah, but you can definitely see that, for example, when you use carrots, it is difficult to get the juice out there. What you usually do is you add a lot of enzymes, or you use a heat crack process. So you heat the mashed carrots up to a certain temperature, which involves a lot of energy.
Yeah.
And the PEF process would only use up to 5 kilojoules per kilo of carrot mash, which is not a big deal.
Yeah, it's
and
small,
the temperature increases maybe 2 degrees Celsius. So that's
so it's again non-thermal.
Non-thermal, very quick.
For the extraction of
exactly.
more yield, more or less, for the juice production.
Exactly.
Very nice. So they also have some. What is that?
I have some horseradish here. So you can not only get the liquid out, but you can see with the liquid also color or other substances can come out. So this is a horseradish that was not treated, that I've put into water. And this horseradish was treated before with PEF. And I've put it into water as well. And you can see that not only juice is leaking out, but also color is leaking out. Which is quite visible here.
Yeah, you can see a little bit on a reddish, pinkish material.
Yeah, exactly. So the color is now going into the liquid, and that's a process that we use for something that is kind of a favorite topic for me, is wine production.
So that process, the same process can be used for wine, and you can, by this means, extract more color or make more colorful wine. Exactly.
When you produce a red wine, what you see when you take a red grape and you cut it in half, most of the color is outside in the skin. So when you squeeze it directly and just ferment the juice is quite pale. You create rosé wines or even white wines out of red grapes. But when you want to create a red wine, you need to leave the skins in contact with the liquid so that you can extract all the color and polyphenols and a lot of flavor and aromas in there as well. And that process can obviously be accelerated by using PEF before. So usually the process would take about up to 2 weeks, and we can cut it by 50%. So we can cut it in half. So if it takes 2 weeks, we can do it in 1 week. Yeah,
1 week.
Roundabout. So
you can increase the speed of wine production.
Yes, especially on the maceration step. So if the maceration is a bottleneck, we can help a lot there. Which also means that you need less energy to pump over during maceration, to mix it, to cool it. That's all reduced.
So that's already this process. I mean, PEF for wine. Already found some applications.
Yeah, we've done industrial scale trials in a wine farm in Spain last year. We're doing more trials this year for the harvesting season, so we're quite busy at the moment. It's looking very good and very interesting. So
some people who might be in the lockdown in Spain might have actually enjoyed the wine with the PEF treated
definitely.
To enhance the production.
Definitely.
Very nice.
You can see the difference here. These are only table grapes, so they don't have as much color as the wine grapes. But I've PEF treated half of it and meshed both of them and put them into bottles and let it sit for a couple of hours now. So this one, you can see that the juice is still quite pale.
It's normal juice.
And you see the color is all in the skins, and here the juice is coming out.
Yeah, I don't know if you can see, but I can definitely, which is also pretty amazing, taking into consideration the damp. Slightly colorblind, but I can see that it's relatively pinkish and darker than this one is pale.
Yeah, we can get some of the liquid out as well, just to show it in more detail.
Perfect.
too much solids in there. So this is the untreated. That's normal. That's quite pale. That's a nice, nice white wine.
To show, but yeah, this is.
That's a nice white wine.
Dark one. Yeah.
Let's get some liquid from this one. There you go.
So
there's a clear difference, I would say. Even if you're colorblind, you can see that.
Yeah, totally. I can see that one is darker and brighter, and that one is pale. I mean, it is
exactly.
Yeah.
So there you can see that you can shorten the processing times, and also create wines that are more, have more polyphenols, which adds a little bit of quality and complexity to the wine as well. There you go. So in the winery, you receive the grapes from the fields. They are destemmed and crushed, and then they would go through the PEF system. The mashed grapes would be pumped through the PEF system, and then going into the maceration tanks. And as one example, we've written down here, the maceration usually takes 10 to 12 days, and we can reduce it by 50% so that we only macerate for 5 to 6 days, but we get a similar or even higher color intensity and polyphenol content in the wine, which is what you want in the red wine, obviously.
Yeah. Definitely.
It's then pressed afterwards. It's fermented and aged, and then you can fill it into the bottles later.
Okay, so the benefits coming from maceration stage and fermentation, aging, which is 30%, 60%.
Yeah, this is a special case where we would treat the lees that are sometimes added into the wine afterwards, like in champagne production, where the autolysis of the yeast would be reduced so that they quicker release certain valuable compounds like monoproteins or amino acids that give complexity to the wine. This is a special case. But obviously you see if you extract more polyphenols in the maceration stage, it also has different opportunities during the aging process, because if there's more polyphenols, they can create more complexes, and the color is stabilized as well. And then obviously before bottling, you could also add PEF to control fermentation, like in the juices, like Claudia explained earlier, which is also...
You mean to get rid of...
bacteria that could still be in there, exactly. Especially for unfiltered wines, that is interesting, because usually all the bacteria are filtered out, but if you want to, you also filter a lot of the flavor out. So you want to keep that in the bottle, obviously, but without the bacteria. That's what we get rid of before.
Unfiltered wine.
Yeah.
It's like unfiltered beer.
It's a trend. It's a trend. You see,
totally.
There's a big trend of unfiltered beer and also unfiltered wine that's coming as well.
Nice.
So it gives a lot of different opportunities to change the processing and make it create more higher quality wines, but also to change the way of processing, shortening processing times, reducing processing temperatures. That all contributes
to sustainability as well.
Exactly.
From all sides.
Exactly.
For timing and efficiency, sustainability, which at the end matters.
Yeah. So if we summarize that, we obviously have a better color and a higher quality based on the faster extraction, as we've explained here. We have more capacity because we can shorten the processing time, which means we also need less energy for this process.
Yep.
And we can create better products.
Yeah.
Using less preservatives.
Very straightforward, very clear, and just maybe next to the olives.
Yeah. Let's do the olives.
Yeah. So you also have olive infographics.
Yes, exactly. We do.
Great.
Yeah. So in a lot of cases, olives are grown close to wine. So that's why this is closely related. Olive oil is produced in almost a similar way like the wine. So you would get the olives from the fields. They are crushed. You create like a olive paste.
Yep.
It's run through the Elea PEF system. Then we have a process that is called malaxation. It's basically mixing and heating up the paste slightly so that you can get the oil out.
Okay.
And this is done at slightly elevated temperatures, usually about 27 to 32 degrees Celsius. And when you open the cells where the oil is contained, if you open that with pulsed electric fields, with the PEF treatment before, you can reduce the temperature. You don't need the temperature to help with the extraction. You can run it at lower temperatures, which means you're using much less energy. We can use 15 degrees. And it's also more gentle for your product. So you create a better high quality.
Room temperature and less, yeah.
Exactly. And you can reduce the malaxation time as well. When the oil comes out easier out of the cells, you can reduce the time. So typically from 60 down to 30 minutes,
Okay.
which again uses less energy and it's increasing capacity. Yeah. And then obviously when you're then decanting usually or separating the paste and the oil, or the water and the oil, and you can get a higher yield of oil in the end. So you get more out of the same amount of raw material.
So high yield would mean less waste. Product usually quite beneficial for,
yeah,
for
and
the
you're
product
also
itself.
shifting towards higher quality. So you get the higher quality oil out. So you, in the end, you're increasing the capacity and you're also getting more of the extra virgin olive oil. So you're shifting from, you usually have different quality grades, and obviously you want the highest quality grades because it sells more expensive and it's better quality. And you're shifting, you have less of the lower grades, but you have more of the higher grades, which is based on the reduced malaxation time and lower temperatures that you can use and the higher yields.
Which is good then, you know, if you have high quality product, I mean, higher quality, more sustainable product, it makes sense to charge more for that.
Of course, definitely.
Should go, and I mean, those company doing that should be supported with, of course, more incentive, more profits, not incentives. It's a very different word.
Exactly. Yeah, you save costs and energy, obviously, because you're reducing the treatment times, and you can process more at the same time because the capacity is higher with PEF. So when it's time for the harvest, it's usually a very short period. Same applies for the wine. So there's a certain point of time where the olives or the wine grapes are ripe, and it's the perfect point of harvest. And then you need to process as much as possible in a short amount of time. So that's helping a lot there as well. And then obviously for the company, it's interesting to get higher profits as well because higher oil quality, because more of the high quality grade, and higher yield as well, which pays for the system itself as well.
So for wine and for olives, do you apply a liquid handling system? So it's a pumpable kind of mesh?
Yeah, we usually...
Or the
Yeah,
hard handling system,
the belt system.
Belt system.
We usually would do that in inline, so we would treat the mesh because it's more efficient.
So
we would pump the mesh, olive paste or mashed grapes through a pipe system. Yeah.
But not the belt, fruit handling systems or what they're trying. I mean, just of curiosity.
Could work as well. I mean, it doesn't really matter if you treat it before or after the mashing. That's no big difference. But in the belt system, there's still water in there that is part of the volume in the treatment zone. So it is more efficient to only treat the mash.
Totally.
Yeah,
absolutely.
Yeah. So it makes more sense in that case, and it's easier to handle as well in the factory normally. When it comes from the destemmer, it's transported anyway, so you can just transport it through a pipe where you apply the electricity.
Nice. So is there olive oil, treated by PEF? I mean, the olive oils treated from the PEF, PEF mesh, from the PEF mesh. Yeah. So is there already? That's how sensitive the information is.
We've run trials in the last harvesting season as well, and that looked very promising. So we're gonna roll that out into the industry.
Okay, sounds great. Okay, then I guess if they don't have more systems, no more questions probably, then we will probably. Oh, thank you very much from our
My
side.
pleasure.
It's very interesting, and also the reddish smell, or you can feel it, that not only the color is extracted, but also reddish smell, which is very nice. So Thank you, and we are going to move on back to Stefan, and we're gonna check some more equipment and machines out there. Thank you very much, and
thank you. Have
see
fun.
you later. Yeah, we will. It was an interesting tour, and we saw a lot of interesting activities and applications for the PEF. But maybe we can look a bit on inside.
Sure, I'm happy to show you the secret part of it. This is where it's all happening. So the potato, as we've seen, fall in here, and on a conveyor belt, they are treated underwater and coming out here. So it's a pretty straightforward, simple setup, filled with water, the vessel here, easy to clean. The water management is automated with a focus on using as little as possible, which means we are measuring the conductivity of the water and only replace it if needed with the amount needed to be operating.
And safety is not an issue, I can see. You know, there are a lot of the safety measures.
Safety is an issue in that aspect that you have to keep the machine closed while you're operating it, but there's a number of independent safety circuits there. Yeah. So yeah, it's kept under control.
And do all machines look like that, or are there different modification setups?
The machines look similar, but when they get larger, they get a little bit wider in the belt dimensions and so on. But I think it's easiest we just take a look at them. So we walk out that direction.
Yeah, totally.
So in here, this is our storage room, Sergey, where we have machines of different sizes, full scale, going from 6 tons per hour up to 50 tons per hour in storage, and they are waiting to be installed at their client's place, which obviously due to COVID sometimes is delayed. Also, or we use our remote maintenance and remote installation tools. We will walk to one of the larger scale machines, a system which is doing 50 to 80 tons per hour in potato industry. So I can show you how such a system looks like and is set up. The whole machine is consisting of 2 parts. The one is the generator part here in the back, and this is where the application happens. So similar than in the machine we have seen before, just a little bit bigger. Here we have an 800 millimeter wide belt, which is able to treat up to 80 tons per hour of potato for cutting improvement. And yeah, this is a big machine, but in comparison to the standard preheating or cooking, it's a much smaller footprint, and obviously, as we discussed before, a much smaller energy and water consumption system.
Okay, Stefan, thank you very much. It's a big pleasure. It was very enjoyable. And now we will go, and Claudia will answer questions from the audience, which we have. See you next time.
Yeah, thanks for showing by. Thanks.